Alright, so today's topic is going to be oxidation, reduction, and this is a brand new unit. So that's exciting. Nothing like a new unit to get you going. So what we did at the beginning of the class was we essentially burnt a couple of things. Okay, so let's examine the combustion of magnesium. Magnesium is a stand-in really for any metal. They'll all more or less do the same thing. They might not all burn quite as excitingly as magnesium does, but under the correct conditions, essentially any metal will react with oxygen in some way. Some, it's very difficult to make that happen, like for gold or platinum, for instance, but you know, under just the right conditions, you can pretty much oxidize or react oxygen with any metal. So let's just look at what's happening here. So we've got magnesium, it's solid metal, and you've got oxygen in the air, it's gas, and you supply some flame, and you end up with this. Okay, this is a reaction that we've seen lots talked about since we were in grade 10, but it's how we're going to actually look at it now that's sort of going to be a little more interesting. Okay, so if we start to think about what's going on here, first, I think we have to balance this, right? So we got to do that and that, and now we have a balanced equation, right? Let's examine this a little more closely here. So what we have, right, is we have an ionic compound that consists of two magnesiums. And each of those magnesiums is going to end up having a positive 2 charge on it, okay? We know essentially why that is from way back when, and that is because if you looked at magnesium and you were able to look at its electron shells, you would see that in its outer shell it has 2 electrons. So it reacts by losing, okay? 2 electrons ends up causing you to have a 2+ charge. Oxygen has 6 electrons in its outer shell, okay? So each one passes an electron or 2 electrons over to oxygen, and you end up with this scenario. Okay? Beforehand, neither of these had any charge at all, right? So over here, magnesium was at a 0, and oxygen was at a 0 in terms of its ionic character. Okay? So what we're sort of going to do is we're going to split this basically into 2 separate kind of parts. All right? So if we look, what we could say is, let's look at just what happens to magnesium. So we'll call this the first half of the reaction, okay? So we see 2 magnesiums, and through the reaction we end up with 2 Mg2 pluses plus 4 liberated electrons. Does that make sense to you, what we saw here? So half of the reaction is basically magnesium liberating or releasing or giving away some electrons from itself. And then the other half of the reaction looks like this. So we have an O2, okay, or 2 oxygens if you want to do it that way, plus 4 electrons. We're going to give you 2 oxygens with 2 minus. Okay. Does that make sense? So something I want you to notice here is if we just look at what kind of charges we're dealing with, you will find that the left hand and the right hand of the reaction always kind of equal out or neutralize one another. You don't pull positives or minuses out of thin air, right? They're always coming from somewhere and going somewhere else, right? So if I look over here, the left side has no charge. And if I add this up, we have 4 pluses and 4 minuses, so this equals no charge over here. Here we have 4 negatives on the left, and here we have 4 negatives on the right. Okay. Now what we could do is we could sum this. So if we were to line here and we were to add the 2 halves of these reactions together, let's look at what you're going to end up with. So you'll end up with your 2 mgs plus O2 plus 4E negative gives you 2 MgO, right? So those sum together plus 4E negative. And we can kind of go through and we can cross those off, okay? And we end up with the reaction that we sort of started with. So you might be saying to yourself, hey, that's great, Mr. Johnson, but didn't you just take something really simple and make it much more complicated for no real benefit? And apparently right now I might agree with you. Yes, this is much more complicated than maybe you're used to seeing for what is really a simple reaction we would have covered in grade 10. However, this skill or this method will become apparent as to why I did that a little farther down the road, okay? So this half reaction concept is going to be pretty important when we're talking about redox reactions, okay? So now let's just take a little step back and talk about what's happened here, okay? So if we look at magnesium, okay, we see that magnesium has become more positive. Okay, it's become more positive. Here it was 0. Here it's 2 plus. It became more positive. And oxygen, here it was 0. Here it's 2 minus. And it became more negative. Oops. Well, more negative. So what does that mean? Okay, well, what are we talking about here? What we're talking about is this concept of oxidation. And I'm going to give you a little acronym, and then we'll talk about which guy was oxidized and which guy was reduced, okay? So it goes like this. Leo says grr. Okay? Leo says grr. So what does that mean? Well, Leo is a name for a lion. Lions say grr. But that's not the end of the story. So these actually stand for something. So what we have here is loss of electrons is oxidation. Down. What do you think the other side says? Gain of electrons is reduction. All right, perfect. Leo says grr, loss of electrons is oxidation. Gain of electrons is reduction. Okay? Loss of electrons is oxidation. Gain of electrons is reduction. So if we look, we can see here magnesium lost electrons, and therefore it was oxidized. Okay? Oxygen gained electrons, and therefore it was reduced. Okay? This is the kind of basic concept behind what we're going to do when we talk about oxidation and reduction. So being oxidized means you lose electrons or you become more positive. Being reduced means you gain electrons or you become more negative. Okay? Later we'll introduce the concept of oxidizing agents, reducing agents. But for right now, let's just leave it as is. Okay? Now, in order to work through this, we're going to learn to assign what are called oxidation numbers. In a case like this, assigning oxidation numbers is pretty straightforward, right? You just see, okay, this became more positive, this became more negative. That's easy. I get that. No problem. But in some cases, it's not immediately apparent whether oxidation or reduction even happened, and then what the oxidation numbers, or whether these numbers changed, or something became more or less positive. So we need to incorporate some rules. So we're going to work kind of backwards. We're going to input the rules, and we're going to examine some reactions to see if we can sort out how to assign what are called oxidation numbers to help us analyze reactions that are not as obvious as this one. Okay? So let's just introduce the concept of oxidation numbers, and we'll go to a different color because it's sort of a new topic. So oxidation numbers. I'm just going to use a little bit of an example here. This is straight from your textbook, but let's start with an example that is not immediately obvious that it's oxidation. In fact, it's not even going to involve oxygen. So oxygen donates its name to the concept of oxidation, but oxidation can happen in many other and with many other elements than just with oxygen. Okay, so if we had some of our magnesium, it's probably true that this reaction was also occurring. During the burning of the magnesium. Okay, we can see here that it's probably, I mean, I think you guys probably know that nitrogen is a nonmetal, so magnesium is also being oxidized here, but it's maybe not quite as apparent as it was before. Okay, so, and it's even less apparent when you're dealing with things that aren't metals at all. Okay, so assigning oxidation numbers will help us work our way through this. Okay, so we'll come back and we'll assign oxidation numbers in a bit. So assigning oxidation numbers can help analyze a oxidation reduction reaction. By the way, they always occur in pairs, right? If something's losing electrons, something else must be gaining them, right? We can't just evaporate into thin air. So this is where you get this concept of redox. So oxidation reduction is often just shortened to redox. Okay? So reduction, oxidation, oxidation reduction always happen in pairs. Electrons have to go somewhere, so someone's losing, someone's gaining. It's just like life. It's a nice metaphor. Okay, think about that. Okay, so basically, oxidation numbers they're related to electrons, but they don't necessarily actually mean the real transfer of electrons from one place to another. Okay, so it's a little bit confusing. So they're kind of like a model or a tool, I guess, to help chemists analyze these sometimes complex reactions. Sometimes they actually do really talk about what's going on, and other times they're sort of a construct. Okay, so let's just look at what we're doing here. So I guess rules for redox numbers. Take the new heading. Okay, so rules for redox numbers. And the first rule is elements in their elemental state always have an oxidation number of 0. Okay? That makes sense, right? They haven't gained or lost any electrons. They have just what they're supposed to have, and they get a number of 0. Okay? In simple ions, a simple ion is just like an atomic ion, not a polyatomic ion. So in simple ions, the oxidation number is equal to the ionic charge. Okay? Maybe we'll do a couple of examples of these. So for here, magnesium, O2, Cl2, N2, etc., all of these have oxidation numbers of 0. Okay? With ions, their oxidation numbers are exactly the same as their ionic charge. Now, when you're writing oxidation numbers, you don't write them like ions, you write them like this. Okay? So these are the oxidation numbers of those ions. So far, nothing too outrageous. Scroll down a bit. Are you guys okay so far? Any questions? So far, so good? Okay. So here's where it gets a little bit more interesting. The sum of oxidation numbers in a neutral compound must be a total of 0. I'm not sure if we should try one right now. Maybe we should. Okay. What if I were to write out something that looks like this? Well, we would know in total, right, the oxidation numbers have to add up to 0. Okay. This might not make total sense just right now, but when you come back and look at it, it probably will. So if we break this apart, right, we know that we have 2 H pluses, and we know that we also have an SO4 that's a 2 minus. Okay? So what we're going to do is we're going to work out what the oxidation numbers on all of these things is. So here we have an ion. What would the oxidation number on this ion be from what we learned before? +1. And we have 2 of them. So 2 plus 1s, right? And right away we can see, okay, there's a 2 minus total over here, okay? So that's how we balance out. That's not really what we're talking about with oxidation numbers, okay? So in a minute we're going to learn something about oxygen, but I'm going to skip ahead. I'm going to say oxygen will always have an oxidation number, or almost always, of -2. Now we have 4 of them in total. So 4 oxygens. So that must mean 4 times -2 is -8. But we have 2 left over. So that must mean that sulfur has a +6. If you work it out, you should find that you end up summing up your oxidation numbers to 0 in this case. So +6 plus -8 equals -2. -2 plus 2 times +1, okay, works out to 0. Are you good? Realize this isn't the most fun thing ever, but you have to learn it. So try to stay with me, okay? The oxidation numbers of all the atoms in a polyatomic ion must add up to the charge on the ion. So that's sort of what I was doing here, okay? Adding up the oxidation numbers to the charge on the ion. Okay, so the oxidation numbers in a polyatomic ion must add to the charge on the ion. Okay. So again, if we go back to the SO4 example. Okay, the total here, -8 plus 6 equals the total charge on the ion of -2. Okay, so there's that rule. And not too much more to go. Almost there, though. Okay. So some rules of thumb. Okay, so these are just elements that you sort of kind of remember to help you along. Okay, so the first is that alkali metals generally, almost always, have oxidation numbers of 1 plus. Alkaline earth metals equal 2 plus, generally, almost always. Okay. Halogens, almost always -1. Oh, but I'm not writing these the right way. Sorry. Oxidation numbers are not written like ions. Let's fix that quick. Okay. Halogens are like that. Oxygen is pretty much always -2. There's one exception. Except in hydroxide, where it is equal to -1. Actually, there's one other place. For OF2, where it is +2. Okay? Which probably makes sense because fluorine is actually more electronegative than oxygen. And what else can I say? Okay, H. Hydrogen is almost always +1. The exceptions to that are except in metal hydrides. For instance, NaH, where it's -1. So +1, -1. And is there anything else? Oh, yes. Fluorine is almost always -1. The only exceptions, yep, when combined with things that are more electronegative, such as F or O. Okay. Let's see if we can do an example here. How about we try a few here? Let's try let's make a little delineation here. See if we can apply these rules into some situations, okay? Let's go with a nice yellow color here. What if we have NH4+? We look at our rules and see what would happen in this scenario. What did we say about hydrogen? It's generally got an oxidation number of what? Good. So +1. Now, how many of them do we have? 4. And what's the overall charge on this? So what does nitrogen have to be then by process of elimination? Perfect. Good. How about this? H2O. Well, what do we know about oxygen? Good. Hydrogen, B+1. And there's 2 of them, and they cancel out. There's a more difficult one here. How about this one? Is that a manganate ion or a permanganate ion? One of the two. Yeah, I think it's permanganate. Okay. So MnO4-. Well, oxygen we said is -2. There's 4 of them, so we should have a total of -8. What's manganese got to be? plus 7, right? Plus 7. Plus 7. Now you'll notice, okay, or I'm not sure if you'll notice, but actually it's the one where I think you will notice. Let's try this. So we burnt some iron before, right? And we may have made this, and we may have made this. Okay, so if we look, we can start to see that the ionic charges on the transition metals sort of work out to be the same as their oxidation numbers. In fact, that's what we were looking at. We didn't really define them as oxidation numbers. But the oxidation states of transition metals, they often have multiple oxidation states. So if you look, in this case, iron's got to be a +2, right? In this case, it's got to be a +3. Okay, so this is where we get this concept that, you know, we can make a +2 ion or a +3 ion. What we're really talking about is the oxidation state of these metals. Transition metals tend to have more than one oxidation state. Manganese does, many of them do. Lead does, cobalt, copper, and so on. Chromium, for instance, they all have these multiple oxidation states that we can work out just simply by applying these rules. Okay, so I'm going to give you a little bit of a chance on a worksheet to work on assigning some oxidation numbers. Where they're going to be used is, if you remember, way back here, we used an example, and we might just want to, before we go on, apply oxidation numbers here and work out what got oxidized and what got reduced. Okay, so we started with 0 and 0. And after, well, magnesium here is a alkaline earth metal, sorry. So we should have a +2 charge, and there's 3 of them, so +6. So nitrogen should have a -3. So if we look, who gained electrons? Nitrogen. So we would say that it was what? Right. This was reduced, or reduction is what happened. This was reduced. And this guy's oxidation number went from 0 to +2, so it was oxidized. Okay. So this is also redox, even though oxygen is not involved. Okay. So we'll stop there.